Happy 300th episode.
I know, it's 7 years.
Not 7 years. It's six. We started it 6.5 because we started in September. So it's 6.5. That's why I say almost 7. But it's not really almost 7. It's really 6.5. But 6.5 was too far to write in the intro bit, so I'm going to say almost 7 years and then go back.
300 episodes.
300 episodes. What we've learned in 300 episodes. Yeah, exactly. Not very much. Almost nothing is what I've decided. Yeah. Okay, so if anyone has no idea what is this that they're watching, we are getting set to record a live episode of Astronomy Cast, which is something that we try to do every Monday at noon Pacific, 3 Eastern, right here on Google+. And so we'll be recording. It's going to take us about half an hour to actually do the show part, and then we'll stick around for a few minutes and answer your questions about space and astronomy, or maybe hear some of your suggestions or some of your insights and some of the big stories that have happened over the last 300 episodes. Cool. Yeah. Now you can ask some questions if you want to contribute. You want to converse with us. A few places you can do that. If you're watching this over on Google Plus on the event page, what's that? Oh, okay. So if you want to do the event, you can comment on the event page, which is sort of over on Google Plus. You can, if you're watching this in my stream or one of the posts that comes out through my stream, you can make a comment there. If you're watching this embedded somewhere on the internet, you can post on Twitter using the hashtag AstronomyCast. Or if you're watching this on YouTube, you can just make a comment there. And in general, the YouTube comment is sort of the safe place to do it, although I know the interface isn't super nice. And YouTube comments, do I need to say anything else? You're muted. Why are you muted?
Yes, I was. I was muted because I was sniffling.
Oh, were you? Okay, all right.
Not everyone needed to hear that. I was just going to say our YouTube comments in general during the live shows aren't too bad.
They're lovely. They're lovely, from real, genuine human beings saying interesting things to each other and us, as opposed to some of the other stuff.
Yeah, there's just the occasional, oh dear Lord, how are you allowed to live comment.
Yeah. This is why we can't have nice things. All right, let me see. Just get everything going here. Recording ready to go. Oh, I know what I need.
Yes.
You're in mono?
Yeah.
Okay, all right. It's been known to not happen.
It's been known very often to not happen.
Why is... Okay. Okay, all right, I'm good. Just needed one last source for comments. Okay. I think I'm good. You're good? You're frozen. The third Pamela Gay.
That was very strange. It demanded my password. It just suddenly dropped out and said, "Thou shalt give me your password."
But now you're back.
And the window's frozen.
You're frozen. Your other version of you is frozen. You need your lower third back.
Yeah, working on it.
She has her lower third. She has her lower third ready to go.
All I see is an avatar over there. So
oh, okay, yeah.
There. Let me add more information to that, though.
I am absolutely seeing technology fail happening.
Yeah, this is one of those new features that Google Plus has introduced, known as the randomly logging you out and forcing you to type your password in. I've seen other people experience it, but this was a first for me.
In the middle of a hangout, yeah.
Yeah.
Yeah. All right.
Okay.
Say
I'm
when.
ready to press record.
Oh, let me get my intro up. Okay, here we go.
I'm pressing record.
Okay, I am also pressing record. Testing, testing. Yeah, it's working.
Except now I'm somehow in stereo. How did that happen?
Oh.
Stop. Okay. Going back to the beginning. Okay, now Mono 1. Okay, recording. And
I am
recording in
also
mono.
pressing. Yeah, I'm also recording. Okay, we're good?
Yep.
Okay, here we go. Astronomy Cast, episode 300 from Monday, April 1st, 2013. What we've learned in almost 7 years. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing?
Good. 300 episodes.
We have gotten a lot of audio out there. That's like 150 hours of audio recorded and edited by poor innocent Preston for the most part.
Well, that's 300 episodes of just Astronomy Cast. And we had the question shows, we've done the weekly space hangouts, we've done a lot. So actually the total amount of audio that we've recorded is way more than that.
And almost all of it is available between our podcast and our YouTube channel. So if you want to learn more, check us out on YouTube.
And do you remember when we first did the podcast, we had like 10 or 20, and people would catch up in a couple of days and then just nag us?
Yes.
These nagging emails like, why haven't you recorded, more? We don't get those anymore.
Oh, for a while we used to actually get it. I logged in at such and such an hour and your new episode wasn't up yet. And that was insane. And now people are more forgiving because we do travel and miss weeks and go on summer hiatus. But 300 episodes.
Yeah, 300 episodes. That's good. That's good. We're getting them out there. And so today, I'll just get into the intro. So we created Astronomy Cast to be timeless, a listening experience that's as educational in the future as it was when we started recording. But obviously, things have changed in almost 7 years and 300 episodes. So today, we'll give you an update on some of the big topics in space and astronomy. What did we know back then, and what additional stuff do we know now? And this is a concept. This concept of the show has been kind of kicking around in our heads for years, and every time we've wanted to go at it, we've both had a really hard time sort of thinking of some of the big stories that have really changed.
Yeah, and I think I don't know about you, but the thing that I found the most surprising that has changed is actually something that's kind of mundane. And for me, the biggest change is just we went from thinking that Jupiter gets hit by a giant rock from space every 500 years to every few months. And that isn't the sort of groundbreaking, let's rewrite the textbooks change that people might expect in 300 episodes.
That's it. That's the big update that you're aware of now, is that Jupiter gets hit more often than... It's
the most surprising thing that seemed least likely to get changed that much.
And I guess, we got a bit of an insight into that with Comet Shoemaker-Levy 9, but then we've since then spotted lots of other rocks hitting Jupiter.
Yeah, there's lots of things that we expect to be, no pun intended, earth-shattering scientific discoveries. Yeah. But the fact that you have a pretty good chance of catching Jupiter-consuming rocks is just one of those things that I think is really kind of awesome in a subtle science kind of way.
So let's kind of do this, peel this like an onion. We're going to start sort of close to home and talk about the Earth and talk about some of the stuff that's maybe in the Earth-Moon system, and then sort of go outward with some of the concepts that that are new-ish. So with the Earth, I think, even with this year, we got hit by the meteor at Chelyabinsk, and that, I think, was a surprise. I mean, it wasn't Jupiter getting hit, but we definitely, and maybe, we've been talking for years and years about the risk, but I think the general public had their eyes opened to this possibility that rocks come from space and crash into the planet and could cause a serious loss of life.
And this is one of those things that you and I kind of disagree on, the importance of, because for me it's like, meh, we knew that was going to happen. Big deal. Phil Plait wrote the book a long time ago. It's all good. But it was a huge news event because of the dashboard cam. Yeah. And so I'm not sure which is more revolutionary, the dash cam or the fact that there were a lot of windows exploded in Russia. it's rocks fall from space, and we get hit periodically.
Well, I think, I mean, I think you're exactly right that, this is no surprise to us. Even how big it is, how often it happens, it's really kind of right on schedule. But I think for me, why I wanted to add this one to the list, and, you under protest, was just that it became the awareness of the whole world, that everybody started to get on that same frequency with us. So maybe we haven't discovered something new, but we have it is now a more of a shared human experience that we should be a little afraid of rocks coming from the sky, and that we should take action to prevent this.
That's true.
Yeah, that's kind of where I feel. So, but let's go to something that we kind of can both agree on, and that is sort of how much water there is on the moon.
World after world, we have over the past several years slowly but surely found progressively more evidence of water. From initially there was radar returns of the moon indicating that the South Pole basins might have water. Then we had Phoenix landing on Mars and digging up ice. We now have Mars Curiosity continuing to find evidence of moisture. And we have messenger and radar returns from Mercury indicating that Mercury may have water. So it's kind of a matter of, if you find something that's permanently shadowed, or Mars and thus cold, you're going to end up finding water there. And that's just kind of awesome, because that opens up whole new possibilities for how easy it's going to be to visit places and produce fuel, hydrogen processes, and potentially even just go and live on Mars. The moon's water is a little bit hard to extract. I don't see that becoming Mars as a harsh mistress type ag stations on the moon, but it's still an interesting future to look forward to.
Right. There are these craters that are in permanent shadow on the moon that you could theoretically build your space colony, your lunar colony on the surface of the moon, and then extract this water from these permanently shadowed craters. But also just, there was these missions that impacted the surface of the moon, and
LCROSS in 2009.
2009, and sprayed up water particles into space, and a lot more than I think they were
now
expecting.
That was kind of overstepping it. It sprayed up a lot of dust, and they did find that there was a few percentage of, by volume, water in that dust, but it was minerals that had water as part of the mineral composition. One thing that a lot of people start to envision is that there are like frozen craters that have like impact residue of comets just waiting. You scrape off the dust, scoop up a handful of ice, and you have drinking water. And that's not the case. This is literally minerals that have water embedded into the minerals, and it would take a lot of energy to extract it out. And luckily, throwing part of a rocket into the moon is a fairly high energy event, and it did allow us to detect that water.
But the amount of water on Mars is a lot more significant than anybody was expecting, and both the current amount of water that's there right now, but also the amount that was there in the past.
And this is one of those things that when we first started this show, there were hints that maybe some of these channels that we see on Mars, maybe they happen to be old riverbeds, but people kept trying to figure out how to explain them using wind processes, aeolian processes, instead of liquid processes, fluvial processes. And so back when we were first starting to get money to go to the Lunar and Planetary Sciences Conference in 2007, we were hearing, well, we're not sure. And people were open to the idea that maybe it was water, but today people just take for granted that these channels we see appearing to flow out of craters are actually created by water flowing out of craters. And when we see these weird craters that look like they splattered stuff all over the place, we're like, yeah, something hit frozen land, melted it, and splattered watery, muddy stuff all over the place. It's now just accepted that Mars is a world with liquids.
And the first evidence from Spirit and Opportunity was very tantalizing, that you saw these kinds of minerals that would only be created within the presence of water. But
Hematite.
now, Yeah, but now with Curiosity, the evidence is just overwhelming that you've got long periods of time that there was, abundant water present on the surface of Mars in a liquid form for a long period of time. And so just the evidence is mounting that not only is there a lot more water just under the surface of the planet now, and again, this is not like, big vast rivers and oceans just under the surface, but like water mixed in with the regolith, down a few feet.
There's some sort of a water table of briny water on Mars.
Yeah. But that there was vast amounts of water on the planet in a liquid form for a long period of time. And this is really exciting and one of the really big steps that we're going to need to be able to find, life, hopefully, with future missions. So,
and Mars Curiosity is happily finding those tumbled river stones and those teardrop-shaped soil deposits from that flowing water. It's straight out geology.
Yeah, and I think on an interesting side note, what we really learned is that spacecraft last a lot longer than anyone was expecting. I mean, we've always talked about how Spirit and Opportunity were supposed to be 90-day missions, and
they were supposed to be dead before we started the show.
They were dead before we started the show, and yet Spirit's now dead, but Opportunity is still going. It's dragging, parts along the surface.
With one wheel lifted.
Yeah. And, Hubble has been repaired and repaired again.
Cassini is another one of those missions that just keeps going and going and going.
Yeah. So I think, that's something that now when the engineers say, well, this is only going to work for 90 days, like unless there's something that's going to run out in 90 days, the expectation is those missions are going to last a lot longer.
Yeah. Herschel ran out of coolant. So Herschel is no more.
Right.
But many other spacecraft just keep going and going and going.
So I think one of the other big surprises, and this is where I think you really need a mission to do the work, is we learned a ton about Vesta. And that was, big thanks to Dawn.
And this was one of those, wow, that came out of nowhere surprises as well. This is an asteroid that we knew was somewhat interesting. It's huge as far as asteroids go. It's one of the top by mass, top by size. And as we studied it from Earth, we were able to realize it had some interesting topography, it had some interesting rotational characteristics. It was worth visiting. But when we got there, what we realized is that interesting-looking crater that we saw on its south pole was the mother of all craters. This is a crater that when Vesta got hit, the entire asteroid crumpled. There's wrinkle ridges. Its rotation was probably altered in the process. And we also learned that there's processes we can't even a priori anticipate that happened. With an object as small as Vesta, you wouldn't expect to find boulders, but Vesta's covered in boulders. So where are these objects coming from? Why aren't they getting flung out into space to become very tiny asteroids on their own? And so we're having to rethink the processes of what crumble, what affect, what wrinkle. What are all the different things you can do to an asteroid that end up producing what we see when we look at the maps that we get from Dawn?
And I think it's great. I mean, again, 7 years ago, we had the best images we had of Vesta were just these hazy radar image, radar scans of it, some radio, Hubble, but really it was nothing more than a kind of a potato, as you call it, far away. But now we've got these images of Vesta done at like, sub-meter scales. It's amazing the level of resolution that we're seeing Vesta with. So it's a whole other world now. And of course, we're on this line because we've got Vesta, but we don't have Ceres yet as of when we're doing episode 300.
But come 2015, we'll have not just Ceres, but we'll also be getting Pluto with the New Horizons mission.
Yeah. So we know that in 7 years from now, we'll at least have two things that we can talk about.
I think by episode 500, we'll be able to cover those.
All right. Cool. Okay, so we've got Vesta. And so then you mentioned Jupiter, and you kind of jumped to the head of the episode with your thoughts about Jupiter. But that is really significant. The fact that Jupiter is smashed a lot more often than we were ever expecting, and kind of has implications for some of the other planets in the solar system too, like Saturn and even us.
And we're still trying to figure out, well, is Jupiter just the safety blanket that protects us from asteroids? Does its presence stir things up more than it protects us? We're still working out all the details. But luckily, the evidence that we're getting hit more often than we thought for Earth isn't there. The 1 in 500 year asteroids appear to luckily be staying 1 in 500, unlike with Jupiter, where it turns out they're 1 in every few months.
Right. Okay. Well, I think we've covered the solar system a bit. Let's move out a bit to the sort of larger Milky Way, our local environment. And I think the big story, I would say one of the biggest stories for the whole, in all of space exploration, really, and astronomy now, is just the prevalence of extrasolar planets. It was, it's not a surprise. If you had told me, 7 years ago.
It's not a surprise for you. For many, it is a surprise.
Well, yeah, because I had but it's serious. I mean, but when we started recording the show, we already knew of a couple of hundred.
Yeah.
100 extrasolar planets. We even did a show on them, a couple of shows on extrasolar planets. But now the number of extrasolar planets is in the thousands, and the variety is filling out our expectations, but also giving us a bunch of surprises.
Right, and here we'd always imagined that stars similar to the sun, stars that are high in metal content, that are middle of the middle of the mass range for stars, so they're not too massive, which means that they give off vast amounts of light, and we thought blew their region empty. We figured stars that were as big as ours and not too tiny, and thus wouldn't have the mass to form planets. We figured sun-like stars probably occasionally, most likely, had planets.
Yeah.
What we're finding is those really massive stars, the ones that we thought blasted their entire region empty, no, they've got planets too. And those little tiny stars that we figured there was no way they could have, no, they've got planets as well.
Too, yeah. Yeah, and big planets and little planets, and planets that are close in and planets that are far out.
The one thing we seem to have gotten right is you do have to be high metallicity. So far, we haven't found any planets in the globular clusters. We haven't found any orbiting your random very low metallicity star.
Oh,
you
interesting.
need to have the high metallicity, but that means our region of the Milky Way seems to be rife with rocks orbiting stars.
Yeah. So have we learned anything new about our supermassive black hole? I mean, I think we were fairly clear that quasars, supermassive black holes, I think we were still on the fence about just what percentage of galaxies seem to have supermassive black holes.
No, I wasn't.
You weren't? No, but now it's very certain that they just all do?
Yeah.
Okay.
Yeah.
All right. Okay, so let's move on to something else then, which is kind of even bigger, is dark matter.
Yes.
And I mean, probably like one of our earliest 10 shows was all about dark matter, and since that time, astronomers have been working hard on trying to figure out what dark matter is. And
we haven't gotten that far in terms of figuring out what the heck it is. We have more and more evidence that it's not some new factor on gravity that we forgot to take into account. But we already knew that from results with the bullet cluster from prior to the beginning of the show, back in 2002, I believe. But since then, using a variety of different surveys, we've been able to start mapping out the 3D distribution of dark matter. So now we understand that more or less it does trace out where the visible matter is located, but there are places where it's at a higher density than the visible matter might cause you to anticipate. There's places where it's at a lower density than the visible matter might cause you to anticipate, but more or less the two follow one another. And it's just really neat to see these three-dimensional structures of how the dark matter is clustered throughout our universe. And these maps have been put together using a technique called microlensing, where you look at how light from objects at a variety of different distances is twisted like going through a carnival mirror by the gravity of that dark matter. And by deconvolving all the mutations that happen to the light, we're able to trace out, well, there's this much dark matter here, this much dark matter there. And we still don't know what it is, but we know where it is.
And there are some really interesting experiments that are gearing up now to really try and sort of answer some questions about what dark matter might be. And, you know, I know there's an experiment, what is it, the Sudbury there's a couple of experiments that are being done to try and get to the bottom of what dark matter is. And they've had some interesting tentative results. So I think we're still 5 years too early to say we've got a, 6 sigma detection of dark matter on what it is. But I think we're close.
It's one of those frustrating things of the detectors just aren't quite there yet. And this was where we were when we started with the Higgs boson. Is when we started the show, there was tantalizing results from the Tevatron up in the Chicago area that maybe Fermilab had detected the Higgs boson. But it wasn't enough of a detection for anyone to actually stand by and say, yes, we have.
Yes.
And so we had hints, and I think we're at that same stage with dark matter of we know what's required to detect it, both in terms of detecting it in an accelerator like CERN, or detecting it in a heavy water detector like Sudbury or Kamiokande or any of these other detectors that are generally used to detect neutrinos. But we don't have the sensitivity yet to say for certain that we know what we're looking at. It's like looking through binoculars that are out of focus and guessing that you can see a bird on a fence post. You're probably right, but for all you know, it's a squirrel or just dust on your lens.
But I think that there's enough resources now. I mean, I think it's that your analogy is perfect with the Higgs boson, which we'll talk about in a second, which is just this, you get these tantalizing hints, and that helps you narrow down the kind of equipment, the kind of experiment that you're going to need to more, better accurately say yes or no to the right level of scientific certainty. And so you get these tantalizing hints that you're going down the right path. Then we follow up with these really much better, more refined versions of the experiments, and I think that's just around the corner. And I will bet that when we have this conversation again in 5 years, 7 years, dark matter will be feeling like it's in that we're pretty sure we know what it is now, or at least what its characteristics are. Yeah.
Yes.
Dark energy, on the other hand, I sort of put dark energy on the list.
No.
We don't know anything else more about it.
No, it's there. That's all we know.
Yeah. It's still there.
It's still there.
Have we defined whether or not
No.
it's increasing or not? Like, are we going to get the big rip or not?
So as near as we can tell, and these numbers are constantly getting refined, as near as we can tell, the amount of dark energy per volume of space has been constant since the formation of the universe. And this is one of those things that just sort of should bother anyone who's ever learned about the conservation of energy, because why is it that as the volume of the universe increases, the volume of dark energy per unit volume stays constant? And that's just troubling. If the universe is getting bigger, then the density of dark energy per unit volume should be getting lower, but it's not. So where's it coming from? Well, maybe it's a scalar field, maybe it's this, maybe it's that. Quiescence has gotten thrown in. We don't know anything other than it's there.
So if you want to know everything we know about dark energy, feel free to go back 6.5 years and listen to our episode then. It's about the same. But let's talk about a different kind of particle, which are neutrinos. And they're, we've discovered that they can change their type.
Yes, and this is actually really good information. So when I started learning astronomy, everyone talked about the solar neutrino problem and how we weren't detecting the neutrinos we should be detecting from the sun. And when I was in graduate school, there was this huge debate of, do neutrinos have mass? Do they not have mass? Well, we think that they're massless. Wait, no, we think that. And finally, we figured out before the show started that they do have mass. And then the fact that they have mass opened up the possibility that the problem with solar neutrinos is they change identity partway to the Earth from the sun, that they bounce between electron neutrinos and tau neutrinos and muon neutrinos. And it turns out that's true. And there's been a series of 3 different experiments over the course of us recording these 300 different episodes. And each of those different experiments has shown neutrinos of a different flavor than what was created, or a different type rather than what was created, indicating that as they travel, they're taking some of their mass and converting it to energy, or taking some of their energy and converting it to mass, and thus changing type.
So take our episode on neutrinos and just throw it out. It's garbage now.
It's not totally garbage.
Right. Yeah, I think I'm trying to remember when we did that one. It was in
we talked
80s.
About the possibility of this happening.
Yeah, done,
but
solved.
There weren't 3 different experiments confirming it yet. So we just had the hints of this is what we think reality is. And
for a little while there, neutrinos moved faster than light, and then they didn't. So
yeah, that one,
they never did. It was a mistake in the experiment. So
it was someone didn't screw something in all the way.
Yeah. All right. Well, let's move on then to the other particle, which is the big one, which is the Higgs boson. And we recorded an episode kind of leading up to it. We have one called the Large Hadron Collider and the Search for the Higgs boson. Now, done.
And what's kind of awesome, and I think has been disconcerting to many of a journalist, is the Higgs boson is just pretty much what we expected. It's a happy little boring particle that isn't doing anything exciting. It doesn't indicate that there's anything wrong with the standard model of physics. It doesn't indicate that there's any supersymmetries out there. And those of us that are kind of content with the standard model, because really supersymmetry is complicated and seems like someone's just making up particles with funky names, there wasn't any necessity for all of the particles in supersymmetry. And the Higgs boson continues to say there isn't any necessity for that. So if there's an underlying physics waiting to be discovered, we haven't found it yet.
So I think yeah, sorry, I was going to move to the next one, but now let me just compose my thoughts here for a second. It's okay. I'm going to keep talking to Higgs. No, I'm going to move on. Okay. Right. So I think one of the other, the earliest shows that we went into, I think it was like episode 4 or 5 or something, was talking about the Big Bang and talking about what we know about the age of the universe and how it expanded and so on. And we were going over and over and over, 13.7 billion years, 13.7 billion years. Turns out we were wrong.
Well, no, I was careful to always say 13.7 plus or minus 0.2. And with those error bars, I was still fine. So this is why you need to use error bars.
But 2013, the Planck Observatory gave us the most accurate measurement of the size of the universe.
And it came out with 13.82 billion. And what's kind of funny is to go back and look at all of the results from further and further years of the Wilkinson microwave anisotropy probe, and then the first results coming out of Planck. And the longer we looked at the universe, the older it got, which sounds obvious at the few years level, but it kept getting bigger and bigger, where from 2004 it was 13.7, then 2010 it was 13.77, and then with Planck in 2013 it was 13.82. And along the way we've also gained baryonic matter. So the amount of normal stuff of atoms and photons and electrons and all the normal stuff that we're used to dealing with, that's gone from an estimated 4% of the universe to an estimated 4.9% of the universe.
So we're still a solid number 3.
Yes.
After what, 27% dark matter and 68% dark energy.
And the amount of dark energy's gone down as well. Yeah. So it's dropped from 72% down to 68.3%.
Not that the amount of dark energy has dropped since we started recording the show, only that the accurate measurement of what it is and has always been is,
we better understand it.
Yeah, we better understand it. So I got sort of one last little kind of speculative thing, which was what would be, some big discoveries, some big announcements, some big advancements that would allow us to overturn some other shows. Let me give you an example. Like, let's say, although Curiosity isn't really equipped to, let's say it does somehow find evidence of life on Mars.
Curiosity can find fossils.
Sure.
I just don't envision life had enough time to create something that would create fossils.
No, but all I'm just saying is that would be the kind of discovery. Or if we, if the search for extraterrestrial intelligence turned up, a signal. So then we could add to the things we now know, there's life on Mars. Things we now know, there are aliens in space. Things we now know, we now understand what dark matter is or what dark energy is. What are some other stuff that maybe, one good experiment, one good result would give us some big answers?
Oh, it's hard to imagine what amazing result would overthrow things, because those are the things that usually come out of left field. The discovery of dark energy is something I don't think anyone could have anticipated. It was one of those factors that we all learned about and then we disregarded and set to zero. And no, dark energy's there. Lambda has a value. Have to redo all of the equations and all of the textbooks. I think if we found life, it would be yes, we anticipated that type of thing nowadays. So I find it hard to imagine, given how closely we've considered the probabilities of different things happening, I find it hard to imagine what would be that real, rewrite all the textbooks, throw out everything you know kind of discovery.
Yeah. Then what is something that maybe you're waiting for more confirmation, that feels in your heart is probably true, and now we're just waiting for a little more confirmation?
I think the one thing we don't know yet is what is the prevalence of life forming where there's liquids. And we have the opportunity, should we ever get ourselves to Europa, to look there. Titan, we can look there. Mars, we can look there. So many different moons around both Jupiter and Saturn have liquid water, we believe, either under their surface or trapped in cavities. And if we could start finding life on multiple worlds, that would tell us it's easy for life to get created. And if we don't find it anywhere, that means it's probably hard. And these start to answer questions about the final issues we don't know anything about with the Drake equation. It still doesn't tell us how long do civilizations usually live. It still doesn't answer the Fermi paradox, but at least it gets us to that, is life common or is life rare? And that's the one we don't know anything about.
All right, cool. Well, happy 300, Pamela.
Happy 300 to you.
And here's to 300 more.
Yes.
All right. Thank you very much.
Thank you. Now don't go away. We're just saving. Okay, I am all saved.
Questions.
Now I know we have some because my phone was going crazy the whole episode.
Paul Gracie wonders if we've done a show on error bars. We
No.
kind of didn't we?
We did some questions show on error analysis.
But I think we did a show on sort of like sigma, like what does we did accuracy.
Yes, that's
right?
true. Yeah.
So Nicole Gallucci, aka the Noisy Astronomer, says, so when you guys started Astronomy Cast, I was a newbie grad student. I actually listened to you guys in between studying for quals. I don't know what a qual is because it was studying light. Qualifying exams?
It's the qualifying exams. It's what allows you to stay in graduate school.
Nice.
Yeah. If you fail them, you cry, and then all your dreams are shattered if you fail them twice.
So Mark Finch wants to know, what do you think dark matter is, Pamela?
I think it's particles similar to neutrinos that we just haven't quite discovered yet. Non-baryonic forms of matter.
Where did they come from? Were they formed in the Big Bang?
That I can't tell you.
Why not?
because that's not my area of
Speculate.
physics.
Speculate. This isn't being recorded. Who's ever going to see this?
See, you exist to speculate, oh journalist, you. I try to ground this in reality.
I was just having a conversation of that with a friend of mine that, that all I need to do to make everything okay is to just go, maybe, it might be possible that so and so, and then I'm just like, whatever. I'm just a journalist. I'm not, I'm not having to explain this. Maybe, possibly. Some say insiders are speculating. Cheshire Tomcat wonders why I said April 1st. That's because we're 4 weeks behind. But we recorded 2 shows last week and 2 shows the week before, and maybe we'll do 2 shows this week. We'll get caught up. Yeah. Insider PWH says, I like the single theme multiple episode series the most, like the history of astronomy and the episodes.
We enjoy doing this too.
Astronomers, scientists, yeah. Though that history series was brutal. Like that was really hard on you. And I know, we try to kind of keep those not happening too often. There's a few episodes that we would love to do, but they would require so much research and so many dates and so much specifics that, yeah.
The ones I really like are where we pair a spacecraft and a human.
Yeah.
Those are the right combination of science, engineering, and history.
Violent Girl says, I know Preston's really busy, but when will the podcast stream be back up to date?
So 295 got edited yesterday. He's going to try and get 296 done this weekend, and I'm going to push for him to get the rest caught up because I know he's getting ready to go on a European vacation.
Yeah, okay.
He's allowed vacations. We just want our episodes. And he just finished his master's thesis, so I know he's been working his butt off.
Yeah. Let's see. Thomas Traneker's notes. Note to self on a trip to Mars, don't forget the rubber duck. So Mark Finch says, thankfully Jupiter's doing a great job of cleaning the system of junk. Is it, or is it, redirecting them at our planet like a slingshot?
We know that in the past, it and Saturn are responsible for flinging things into the inner solar system. What we don't know is today, does it do more harm or more good? So this is planetary dynamicists are always working on trying to argue that one out.
Eric Charlotte opened a beer in celebration of episode 300. Yay. I wish I could do that, but that would be irresponsible of me. Maybe later tonight.
Yeah, I'm sticking to my diet sodas.
I just think, you don't want to be that drunk when you record. When will the podcast image ever be fixed? Which podcast image is broken? The one in maybe the one in iTunes I think might be broken.
Okay. If you can work on sorting that.
Rod Mole says, can you recommend a good book on the Fermi paradox? There was a book that came out a couple of years ago that was like 100 solutions to the Fermi paradox, something like that. And it was good because it, tried to go the other way around and kind of go, well, maybe it's this, maybe it's that. Let me just find it. Unsettling and unhelpful, and here it is. Where is Everybody? 50 Solutions to the Fermi Paradox. It was written by Stephen Webb.
Okay.
Back in 2002. It's if the universe is teeming with life, where is everybody? And I haven't read it, but that was sort of on topic.
Yeah, I haven't read it either.
Yeah. What else? I think that's it. I think I've gone through all the questions.
We're going to be doing a My Moon discussion. And we're going to have actually, I believe, an artist on, a musician, I think. Then Wednesday night with Learning Space at 4 o'clock Pacific, we're going to have a couple of the Dawn team scientists come on and we're talking about Vesta mappers and Vesta science results. Thursday is the Planetary Science Hangout. Friday is the Weekly Space Hangout. And really, I'd encourage all of you, go check out our YouTube channel. Last week, Nicole Gugliucci and I put in a ton of time in getting the whole YouTube channel cleaned up, brought up to date, and you can find everything in a logical manner there. Now, some of the episodes, the editing at the beginning and end still needs cleaned up, but they're all there. So please go subscribe, go learn everything you can about the cosmos.
Awesome. Okay, cool. Well, then I'm gonna wrap this up. So again, congratulations on 300 episodes. That's awesome. That's cool.
And let's just keep doing this.
We'll keep rolling. We can do this. We can do this forever till you guys get sick of us. All right. We'll see you later, Pamela. And thanks everyone for watching. And recording ready to go. Oh, I know what I need.
Yes.
You're in mono?
Yeah.
Okay. All right. It's been known to not happen.
It's been known very often to not happen.
Why is... Okay. Okay. All right. I'm good. Just needed one last source for comments. Okay. I think I'm good. You're good? You're frozen. The third Pamela Gay.
That was very strange. It demanded my password. It just suddenly dropped out and said, "Thou shalt give me your password."
But now you're back.
And the window's frozen.
You're frozen. Your other version of you is frozen. You need your lower third back.
Yeah, working on it.
She has her lower third. She has her lower third ready to go.
All I see is an avatar over there. So
oh, okay, yeah.
There. Let me add more information to that, though.
I am absolutely seeing technology fail happening.
Yeah, this is one of those new features that Google Plus has introduced, known as the randomly logging you out and forcing you to type your password in. I've seen other people experience it, but this was a first for me. In the middle of a hangout, yeah. Yeah.
Yeah. All right.
Okay.
Say when.
I'm ready to press record.
It's about half an hour to actually do the show part, and then we'll stick around for a few minutes and answer your questions about space and astronomy, or maybe hear some of your suggestions or some of your insights and some of the big stories that have happened over the last 300 episodes. Cool. Yeah. Now you can ask some questions if you want to contribute. You want to converse with us. A few places you can do that. If you're watching this over on Google Plus on the event page, what's that? Oh, okay. Yeah. So if you want to do the event, you can comment on the event page, which is sort of over on Google Plus. You can, if you're watching this in my stream or one of the posts that comes out through my stream, you can make a comment there. If you're watching this embedded somewhere on the internet, you can post on Twitter using the hashtag Astronomy Cast. Or if you're watching this on YouTube, happy 300th episode.
I know, it's 7 years.
Not 7 years. It's 6. We started at 6.5 because we started in September. So it's 6.5. And that's why I say almost 7. But it's not really almost 7. It's really 6.5. But 6.5 was too far to write in the intro bit, so I'm going to say almost 7 years, and then go back.
300 episodes.
300 episodes. What we've learned in 300 episodes. Yeah, exactly. Not very much. Almost nothing is what I've decided. Yeah. Okay, so if anyone has no idea what is this that they're watching, we are getting set to record a live episode of Astronomy Cast, which is something that we try to do every Monday at noon Pacific, 3 Eastern, right here on Google Plus. And so we'll be recording. It's going to take. You can just make a comment there, and in general, the YouTube comment is sort of the safe place to do it. Although I know the interface isn't super nice, and YouTube comments. Do I need to say anything else? You're muted. Why are you muted?
Yes, I was muted because I was sniffling.
Oh, were you? Okay, all right.
Everyone needed to hear that. I was just going to say our YouTube comments in general during the live shows aren't too bad.
They're lovely. They're lovely, from real, genuine human beings saying interesting things to each other and us, as opposed to some of the other stuff.
Yeah, there's just the occasional, "Oh dear Lord, how are you allowed to live?" comment.
Yeah. This is why we can't have nice things. All right. Let me see. Just get everything going here.